The formula that you will use in determining interfacial tension is empirical in nature, and it can only be and it will only have acceptable values if the argument of the Ln here, you could see that you have x sub AB plus x sub BA plus x sub CA plus x sub CB divided by 2, meaning these two are averaged first and added to the sum of x sub AB and x sub BA. Now, if the argument of this Ln, since it's the argument of your Ln, is on the range 0.0004 to 0.3, then the value that you will be getting is acceptable. So it says here, equation holds when value of the argument of the Ln function is on the stated range. Now, a value of 1.0, indicates that there is rather complete solution of the phases at the plate point. So meaning there's no two separated layers that are formed when the value of this L1, the argument Ln of 1 is 0. So if the value is 1, then we will have an interfacial tension which is negative. And that tells you specifically that your interfacial tension is not acceptable because we don't have an interfacial tension that is negative. So then your solution is, it's near impossible, if I may say, it's really impossible for separation to happen because there is complete solution of the phases. The phases that are being referred to in here are your raffinate and your extract phases. So your extract phase carries the component of interest from the feed, and your raffinate, of course, has the rest of the components which were not extracted. Okay? A range of values of interfacial tension is 4 to 52.5 dyne per centimeter if you're going to use this empirical equation. Okay, this is the expected value. And I have placed in here the necessary conversion factors that you will use if you are dealing with problems using English units. So since what you'll be able to get from property tables for interfacial tension, the unit is in dyne per centimeter, there's a need for you to have it converted to the unit pound mass per hour squared if you are using, or if the problem is using English units. So this is the appropriate conversion factor. And I think you have also seen this in the solution that was shared to you last meeting in terms of determining the size of the column and in the height of our column. Okay. Now there's also this particular conversion. I place it in here as well for viscosity in centipoise. Most property tables have viscosities in centipoise. So if again the problem is using English units, there's a need for you to have it converted. So this is your conversion factor. Okay, for dyne per centimeter, this is your conversion factor also. Now the problem that I placed in here, sample problem number 5, is exactly the same actually as the sample problem shared by John Kuplis in his book on principles of transport processes and separation processes. In here, you are to estimate the interfacial tension given the set of data points. Now, the water-rich layer and the MIBK-rich layer have the following composition. So, the water-rich layer, by the way, is the, so if a short review, when you speak of the water-rich layer, this is the what. And when we speak of the MIBK-rich layer, this is the what. In terms of the layers that are formed during liquid-liquid extraction. So the water-rich layer is the, we have mentioned this also in our last discussion, it is the what. And by the way, our system here, which produce the two layers, the water-rich layer and the MIBK, methyl isobutyl ketone layer, consist of water, which is A, acetic acid, which is C, and methyl isobutyl ketone as the B. So I'll go back to my question because this was already covered in our previous discussion. When you speak of the water-rich layer for a liquid extraction process and a solvent-rich layer, your MIBK here is the solvent-rich layer. What are these layers, by the way? So they are referring to the what? We only have two layers produced after equilibration of our feed with the solvent in the process of extraction. So water-rich layer is referring to the what? The water-rich layer and the uh, solvent-rich layer. They are referring to the what? We forgot already. I mentioned this and I really recall mentioning this in our discussion. When we speak of the water-rich layer, that's the raffinate layer. When we speak of the solvent-rich layer, that's the extract layer. So they are the two layers produced after equilibration of our feed with the solvent. So in this case, for our system, water, acetic acid, and methyl isobutyl ketone, you are asked to estimate the interfacial tension given the composition of the water-rich layer, or that's the A layer, and the MIBK layer, which is the B layer. Now, I'm specifying that water-rich layer is A and MIBK-rich layer is B because that has something to do with the way you use the formula in here. The formula in which you have the X sub AB, you have the X sub BA, CA, and CB. Okay, all of which are X. So what are these particular X's with the corresponding subscripts? So by the way, they represents the mole fraction. So in here, this represents, for example, let me just annotate so you will see. In the case of X sub AB, this represents the mole fraction of A in the B layer. So whatever is the A as defined by the problem. So if the problem does not specify the A must be referring to the solute. Now, the X sub BA, on the other hand, is the mole fraction of B, whatever B is, in the A layer. That's the same thing with this. Mole fraction of C in the A layer and mole fraction of C in the B layer. Now, if you can also recall again, when we speak of liquid-liquid extraction, our concentrations are not in terms of mole fraction, but rather they are mass percentages. So there's a need for you to convert the percentage by mass given in the problem. It's a given. Meaning if you'll be given a concentration table, just like the one that I have shown a while ago in the problem, there's no need for the to indicate what is the concentration or how is the concentration. Why, or shall I say, there is no need to specify what is that particular concentration. Because when we speak of liquid-liquid extraction, that is percentage by mass. The other unit operations, it's mole fraction or percentage by mole. Okay, mole percentages. Okay, so that's it in this formula, mole fractions, not mass fractions. So there's a need for you to have it converted. The first letter in the subscript tells you of the mole fraction of that particular component. The second letter tells you the location. So in this case, the mole fraction of A in the B layer. Okay, now if you're going to use that particular formula, this empirical formula in here, there's a need for you, as I've said, to convert the mole fraction, the mass fraction to mole fraction. So I'll give you an example on how you do it on one, and then the rest you can do on your own because the rest will just be substitution to the formula. So just give me a few minutes to open the Jamboard so I can show to you the process. So I'll go to our Jamboard now. And determine the X sub B. So remember that this is mole. This is mole fraction. So you could see in the B, okay, I wrote here BA. So meaning you're going to use the first set of columns, the first three sets of columns, because what I wrote here is determining the composition of B in the A layer. Actually, you're also going to determine the composition of A in the B layer. Excuse me. So in this case, you go to the first three sets of columns and you use the data in which the second row data in which you have the complete, you have all three components complete. There's no zero concentration for A, B, and C for the first three sets of column because that refers to the A layer. I'm after for the composition, the mole fraction of B in the A layer. Now, you could see that B there is 1.7, but that is mass. That's the percentage by mass. If we assume that our solution containing A, B, and C is 100%, and it has to be 100, so then this 1.7 is already in mass. Now, if you have it converted to moles, you need to divide it by the molecular weight of, that would be the B. In this case, our B is, if you have taken a screenshot, it's methyl isobutyl ketone. B is methyl isobutyl ketone, and it has a molecular weight of 100.16. Now here in the denominator, you have already converted the 1.7 mass to moles. You do the same here in the denominator, but this time all three component number of moles will be placed. So you have 1.7 divided by 100.16 plus, okay, we need to add that of water. So water is 95.46 and it has to be divided by 18 because that's the molecular weight of water. And we have acetic acid, which is 2.85. The molecular weight of which is 60.05. So these are all in moles. The mass values of the three components were now converted to moles. So this is the total number of moles in the denominator, and the numerator is just the number of moles of B. B, which is our methyl isobutyl ketone. Now for this one, you will have an answer equivalent to 0.003163. Okay, now you do the same procedure in determining the X sub AB. Okay, the same procedure for X sub AB. So you will now be using the B layer, meaning that the last three columns, and you will be using A, and A is water, and you use the second row, by the way, because that's where all three components are present. So in this case, I'll divide this by 2.8. You divide it by 18. Okay, that would be A, which is water. So that should be appearing here in the denominator. And then after that, you will have to consider the presence of the acetic acid. You divide it by the molecular weight of the acetic acid. And last would be the MIBK, which is 95.33. Need to divide it by 100.16. Okay, that's the mole fraction of A in the B layer. So kindly check if the information that I placed in there is correct based on the second set of three columns, referring to the B layer composition, specifically the second row, because that's where all three components are present. Okay, if you'll do your mathematics here, your answer would be 0.1365. And if you repeat the same procedure for X sub CB, your answer would be, will not anymore place the process, 0.02736. And for your X sub, what else do we need? CBCA. Your CA is 0.00885. Just a moment, class. Now, with all the four already complete, we can go back to the formula. Here, our formula, I'll transfer to our slide. So our formula for determining interfacial tension is this. So the four mole fractions, you just substitute in here and you determine the interfacial tension afterwards. So in this particular problem, if you have to do that, your answer for the interfacial tension is 8.65 dyne per centimeter. Okay, 8.65 dyne per centimeter. So if the problem is asking for the interfacial tension, that would be your answer. So just don't forget that the second letter here is the layer, which you're going to use the composition of your component to determine its mole fraction. Okay. Any questions? Okay. So I hope everybody gets it. Now we go to perforated plate, or we refer to that as the sieve tray extraction tower. Okay? And since we're talking about the different equipments used in extraction. Now these are similar to sieve trays, these perforated plate extraction towers, and these are the same thing that is being used in distillation and absorption. Now, the tray holes here, since it's a perforated plate, so the plates have holes, the diameter ranges from 0.32 to 0.64 centimeter in diameter. And if you're going to take the sum of all these open spaces, meaning you take the sum of the areas of these tray holes, it should only constitute 15 to 25% of the total tray area, referring to the sum of the areas of the holes. Now, how are the trays spaced? So the spacing is 10 to 25 centimeters. Now, in terms of the efficiency, the fractional tray efficiency for this extraction towers, you're given the formula in here, 0.352 T raised to 0.5, then divided by the sigma, the interfacial tension, D sub O raised to 0.25 times the ratio of the V sub D and V sub C raised to 0.42. Now, the variables that you see here are defined here on the next, on the column in here. So, your sigma is interfacial tension, dyne per centimeter. Your T is the tray spacing in feet. The D sub O is the whole diameter of your perforations in feet. And the V sub D and V sub C refers to the linear velocities of the dispersed and continuous phases. Okay, now take note that your interfacial tension is SI in units, so it's in dyne per centimeter, where the rest of the units are English. So whatever is the specified units for all these variables here in this formula, it should be followed because this is empirical in nature. So there's no need for you to convert the interfacial tension in dyne per centimeter to pound mass per hour squared, because it just so happened that the rest of your variables here are in English units of feet or feet per second. Its set of units referring to the interfacial tension stays with the original set of units dyne per centimeter. Okay, that's for our perforated plate or the sieve tray extraction towers. Now, it has high capacity, so 30 to 50 cubic meter per meter squared per hour. Good efficiency due to minimum back mixing. Multiple interfaces can be a problem because there will be formation of several interfaces in here. Now, it has limited turn down flexibility. So meaning whatever is the expected output based on a particular flow rate of the feed that is to be processed, that would be it. It's not as flexible as the other extraction equipments. Now, this can be easily affected by changes in wetting, meaning how well is your, shall I say, how well is your descending continuous phase wetted by the solvent that is dispersed, flowing upward counter current against it. Okay, so it's easily affected by changes in this wetting characteristic. Now, limited as to which phase can be dispersed. So as per design, normally as per design, what is dispersed is the solvent and the feed is the continuous. So if in a particular sieve tray extraction tower, your solvent is really the dispersed phase, it cannot be the other way around, because if you notice in a previous problem that we have discussed, there was a question of what if you interchange the phases. Your toluene was made as the continuous phase and your water was made as the dispersed phase. It's the other way around. Dimethylamine, I think, not water. So in that case, in the case of sieve tray extraction tower, you cannot interchange. If it's designed that the dispersed phase is the solvent phase and that's it, you cannot have it interchange. Now in here, in sample problem number 6, you are given an organic solvent that is used in extracting acid from water in a perforated tray tower. The dispersed organic solvent flow rate is 600 cubic feet per hour and the continuous aqueous flow rate is 400 cubic feet per hour. So notice, it says the dispersed organic solvent. So it's always the solvent that is being dispersed, and your continuous phase, which is of course your solute in water, is the one that is your feed, or your feed is the continuous phase. Now, you're given the interfacial tension in 15 dyne per centimeter with a tray spacing of 1.1 and a hole size of 0.4 centimeters. Estimate the tray efficiency, and it asked what will happen if the solvent rate is reduced. So what will happen to our extraction process if the solvent rate is reduced? I'd like you to take a screenshot of that particular problem. That way you can provide me with the information as we transfer to the Jamboard for the solution of this problem. Just a moment, class. You could see in here that in terms of the tray efficiency, this will be your guide formula. Okay, this is the guide formula that you will be using. So kindly take a picture as well of this one so you can supply me with this formula when we go to our Jamboard for determining the tray efficiency. Okay? And take note, anyway, if you take the screenshot, you would still see the set of units that we should follow for all the variables that appear in this equation for determining our tray efficiency. Okay, I'll go to our Jamboard. And I'll just go straight to the formula for the tray efficiency. We have E sub O. Are we able to get the formula? Can you please supply me with the formula? The formula that you took a screenshot of for the tray efficiency is
0.352.
yes, T raised to 9. And
Yes.
You have the sigma. You have the diameter of the tray hole. And you have here the ratio of the dispersed and the continuous phase flow rates. Actually, class, this could be flow rates, this could be velocities, either of the two will do. Okay, so raised to 0.42. So in terms of the problem that we have, you just need to place in here the value.
Miss.
Yes.
0.25, I think, miss, instead of 0.35.
Okay. Uh, I did have a typographical error there. Okay, you change, anyway, you change the copy. If you have your copies already, please change the exponent of the D sub O. I have beside me the book. It should be 0.35, not 0.25. Maybe I mistyped it when I was copying the formula. Okay. Now, the tray spacing. What's the tray spacing in feet for our problem? What is our tray spacing? Were you able to get it?
1.1, miss.
1.1.
Yes, miss.
So it's 1.1 and it should be in feet. So if it's in feet, that's okay. You raise that to 0.5. Your sigma should be in dyne per centimeter. What's your sigma?
15, miss.
In. I will not anymore place the units anyway, as long as we adhere to the specified units. The tray hole diameter is
0.40, miss.
40.
0.4, miss. Yes, miss.
Okay, what's the unit?
Centimeter, miss.
Okay, so there you go. It's in centimeters. So I'll place here centimeter because as based on the formula, if you took a screenshot of that, it should be in feet. So you need to convert the centimeter into feet. So you have 2.54 centimeter in 1 inch, and we have 12 inches in 1 foot. Okay, you have that. And in our numerator, we're okay here. Then we have the V sub D. So your V sub D is the flow rate of the continuous phase. What's your flow rate for the continuous phase?
400, miss.
400. And what about for the dispersed phase?
600, miss.
600. And you raise this to 0.40. And that's it. This is how you determine the tray efficiency for the perforated tray tower. Okay, what's your answer? What's your answer, class? This is efficiency, so our answer should be less than 1. Johan here gave 0.133. Kindly check if you get the same answer as well. Let me check on my calculator. By the way, this should be raised to 0.35. I missed something here. Are you doing the calculations as well in your end? What's the answer? Okay, what Johan gave me is correct. So that should be 0.133. Okay, for that would be now your tray efficiency. Now let's go back to our slide and check the question that is being asked. What happens if the solvent rate is reduced? So what will happen if the solvent rate is reduced? Meaning your V sub D is reduced. The way to answer the question is you go back to the solution. Okay, let's go back to our solution. Now what will happen if the dispersed phase, that's your solvent, is reduced? So what will happen to the tray efficiency if that is the case? If V sub D is reduced, what will happen to the tray efficiency? Greater siya. What about the others? Will it grow bigger? Will it be smaller? If this B sub D is reduced, what will happen to the, of course. Okay, so I have one already giving me the correct answer, or two. Since your V sub D is in here, if this is reduced, the entire value of the computed efficiency will also decrease. So it will also be reduced. So answering the question is based on the formula. And where is the dispersed phase in the formula? Since it's being multiplied here to this expression, if it's being multiplied and it's being reduced, then you expect the value of the tray efficiency to be reduced as well. Okay? Now I go back to our slide. Okay, now we proceed. So we go now to the pulse tower, extraction tower. So in here, there is this form of pulsation for your tower. Its capacity is acceptable, 20 to 30 cubic meter per square meter per hour, not as much as the previous one. This one, the sieve tray, because it's 30 to 50, while this one is just 20 to 30. Now, what is special about this pulse extraction tower is it's best suited for nuclear applications, since it does not have any seal due to the lack of seal. Now, suited as well for corrosive application when constructed out of non-metals. So if it's constructed out of non-metals, then in terms of having to worry about whether there will be corrosion problems, then we reduce that one. There won't be any corrosion because the material itself that was used is a non-metal. Now, limited stages due to back mixing. So we don't expect this tower, this extraction tower, to be tall due to back mixing, and limited diameter and height due to pulse energy required. Since there's a certain degree of pulsation in the tower, we cannot make it as big and as high as the usual sieve tray or perforated extraction tower. This pulsed and sieve tray tower, the last two towers that were discussed, are towers where mechanically or some form of mechanical agitation is designed with it to increase mass transfer efficiency. The mass transfer efficiency is the throughput, the degree of the transfer of the solid from the feed to the solvent that has something to do with the throughput. Now, what about the pulse pack tower? So there's a degree of pulsation. It's using packing material. So in here, you expect a reduced HETS value. If you can still remember the HETS, the height equivalent to one theoretical stage. And the decrease is by a factor of 2 or even more. Now, this is for liquids with high interfacial tension. So the range of the interfacial tension in here is from 30 to 40 dyne per centimeter. Now, this one is pulsed pack tower. We can also have pulsed sieve tray tower. The sieve tray or the perforated tray tower, the standard that we have discussed a few minutes ago, it can also be pulsed. So in here, the hole size is reduced to 0.32 centimeter. And in terms of the free space, it's 20 to 25%. Okay, 20 to 25% and 5.1 centimeter tray spacing. No, so not as, shall I say, widely spaced as the original sieve tray towers. Now, the trays occupy the entire cross-section of the tower and there are no downspouts that guide your liquid, or that is your feed that flows downward countercurrent against the dispersed solvent. So we can have, take note, pulse pack towers. So similar to the pack tower that was discussed a few seconds ago. So it could be pulsed, and we can also have pulsed sieve tray towers. Now, our towers can also have some form of agitation, mechanically agitated extraction towers, and you can read this as well in John Cookle's or in McCabe, the Shebel Tower. Now, this uses rotating turbines, turbine agitators with outer setting zones. Now, this operates in a series of mixer settler extraction units. So you have a mixer and then there's a settler that follows. If you recall my discussion at the start of liquid-liquid extraction, the simplest form of an extraction equipment is that you can have a mixer to homogenize your feed and your solvent, and then you will have the setting zones, or shall we say the separator. So you can see here settler, the separator, because one of the faces settles and the other one is on top on it. So you have a mixer settler extraction unit, and they can be so arranged that they'll be adjacent to each other, one on top of another. Now, reasonable capacity of 15 to 25 cubic meter per meter squared per hour, high efficiency due to internal baffling. Baffles are simply guides on how well fluid flow down the column. Since it does not have any downspouts, then this time the thing that guides the fluid as it goes down is the baffles. Now, good turn down capability, so 25%, it's already good, meaning the transfer of the solid to the solvent is expected to be 25% or even more. Now, what is the best application for such a special type of extraction tower? Now, best suited when there are many required stages for the extraction to achieve its shall I say, recoverability. If we need a high recoverability for our extraction, then this is the tower. This is the extraction equipment to use. Not recommended though for highly fouling systems or systems that tend to emulsify. Or shall I say systems, colloidal systems, they tend to emulsify. So this particular extraction tower is not recommended for such systems. Now we can also have the mechanically agitated towers also under it. Aside from the Shebel tower is the car reciprocating plate tower. The form of agitation is not in the form of a stirrer. So the system inside is not agitated in the form of a stirrer, but in this motion here, the going up and down of the plates. You can also read this in our text. The car reciprocating plate tower. So your tray holes is 1.4 centimeter. The open space is 50 to 60 centimeter. The biggest of all so far, extraction towers. Open space meaning if you sum up the areas of the holes, it would be 50 to 60% of the total tray area. Plate spacing is 5 to 15 centimeters. Highest capacity so far. So open space is the highest, also highest in capacity. 30 to 60 cubic meter per meter squared per hour. Good efficiency, good turn down capability, 25, the same as the Shibel Tower. Uniform shear mixing, and best for systems that emulsify. So if you have a problem with the Shibel Tower because it cannot handle systems that emulsify or colloidal systems, then this is the tower to use, okay, for that particular application for that requires it, okay, specifying that it's for systems that emulsify. Now we're done with the different towers, extraction towers, and we can go to our multi-stage countercurrent extraction system. So multi-stage, you have several stages connected adjacent to one another. This is the representation of John Copley's in terms of the overall mass balance. Our feed is L sub O. Our solvent is B sub N plus 1. Our extract is B sub 1 since it's leaving stage 1. And our raffinate is L sub N since it's leaving stage N. Okay? If we make a balance on the solvent C or in the solute A, the material balance that you have here, the overall material balance that you have here only needs you to multiply each of the phases that appears in the overall mass balance by the corresponding mass fraction or weight fraction of each of the phases. So if it's C, then your L should be multiplied by X sub C O, L sub O specifically. We use X for the liquid or for the feed, and we use Y for the solvent, okay? And we use the letters A, C, and B for A solute, C solvent, and B for the solvent, the carrier solvent of your solute in the feed. That's our B. Most of the time, it is water. So you can see our material balance here. It's L sub O plus V sub N plus 1 equal to L sub N plus V sub 1 equated to the bulk phase M. Now, if it's interpreted graphically or represented graphically, your L sub O is plotted on the triangular equilibrium diagram using the concentration of A and C. So this is the A and this is the C. So most of the time, the L sub O is in here at the bottom of the phase envelope, this curve. And most of the time, but not all the time, your solvent is pure. So if it's pure, then it's right on the apex of this triangle, since any point in here represents 100% C, whatever C is. So you can see here the solvent V sub N plus 1 is right on the tip of the triangle, and this is your L sub O. Now this is the bulk phase M, and this bulk phase M is the point where the composition, the resulting composition of the feed and the solvent that gives out rather the resulting composition of the feed and the solvent. So this would be your M. As discussed previously, the tie line connecting V sub 1 and L sub 1 should be passing to the lower part here. There is a rectangular, if you can recall, we have this rectangular diagram here. Rectangular diagram, you have your 45-degree line, and let's say you have your curve here. So your V sub 1, if you go down, you turn left and you go up. You go until here only because this is already V sub 1. Let me just erase. So if you go up, erase everything. Let me repeat. So you go down, you turn left until you reach the 45-degree line, you go up and rest on the lower part of the face envelope. This is your L sub 1. Okay, telling you that the V sub 1 and the L sub 1 phases are equilibrated because you're using the lower part here, the rectangular equilibrium diagram, to have them connected. If you connect these two, the L sub 1 and the V sub 1 points, it should pass through the end, the bulk phase end. Okay? And then you connect this L sub 1 in here to the at 1. So if you will have here your V sub 2, the same thing. You go down, you turn left, you have here, and you have L sub 2. And L sub 2 and P sub 2 will be again another tie line. Now, that's the graphical way of determining the number of stages, because we determine the number of stages based on the number of tie lines that we have made. For example, this one, the L1 to P1 tie line, that's one stage. So this is graphical, but we will not do it graphical. We will solve it using Krebser equation. So that's how they do it in determining the number of stages graphically. Okay, so the mixture point or the bulk point M is where your L1 and B1, the equilibrated phases, will pass through. And it's the same bulk phase where LO and the feed and the V sub M plus 1, the solvent, is going to pass through. I suggest you read more on our textbooks on the graphical way of determining the number of stages. That way, you will have an alternative if, let's say, you have difficulty having to process everything using Krebser's equation. Okay? Now, we will proceed. So this is our sample problem number 7. It is asking you to determine the compositions and the amount of the extract and the raffinate layer. Okay, we'll have a 5-minute break. You need a 5-minute break. You can also take your break. We'll go back here after 5 minutes. An aqueous speed of 200 kilogram per hour. So aqueous meaning the carrier solvent is water for your solute. It contains 25 weight% acetic acid. And here, pure isopropyl ether is used to extract acetic acid. Now, the rate is 600 kilogram per hour for this solvent, and it is counter current, and this is for the multi-stage system. So the exit acid concentration in the aqueous phase is to contain 3 weight% acetic acid. Calculate the compositions and the amounts of the exit, extract, and raffinate layer. This is similar to a problem that I discussed to you, but that particular problem is just single stage extraction. The only difference for this one is multi-stage extraction. But the thing is, the process of determining the required information is very similar. So I'd like you to get a screenshot of the problem so you can supply me with the information if you go to our Jamboard already. Okay, so I'll now share our Jamboard. So this is our given. Okay. You are given what information are you given? 200 kilogram of L sub O having 25 weight% acetic acid. So if you're going to have it like this, you can have it like this, or you can have it drawn in the form of a column. You have here L sub O, you have here B sub N plus 1, you have here L sub N, you have here B1. Okay? Of course, you have this one, and I'll just place here a dot. This is your last. And the way our arrows here should be opposite. Okay, this is stage 1, let's say, and this is stage N, and the end stage, and this is stage N, the last stage in our multi-stage equipment, extraction equipment. You have 200 kilograms containing 25 weight percent. So this is 200 kilograms per hour. If it has 25% acetic acid, so this is 0.25. Okay, what else is given in the problem? Can you supply me with the given information? What is our V sub n plus 1?
600.
600 kilogram per hour. This is pure. This is pure, what's our solvent? Pure isopropyl ether. Is it pure isopropyl ether? Your solvent?
Yes, miss.
Okay, so the amount is 600 kilograms per hour. The exit acid concentration in the aqueous phase is 3%. What is this referring to? The exit acid concentration in the aqueous phase is 3%. What is this? If you're going to represent this in our illustration here, what is that? The 3% acetic acid. Where am I going to place it? I have 4 phases here, the LO, the L sub N, the V sub N plus 1, and the V sub 1. So if it's saying that the exit acid concentration in the aqueous phase is to contain 3 weight percent acetic acid, how is it supposed to be represented to? Or where will I place it in our illustration? That should be the X sub AN. Okay, very good, John Albert. So your 3% is the X sub AN. It's referring to the raffinate exit stream. This raffinate is to contain 0.03, that's 3% acetic acid. And that's it. Would you like to add anything more on the problem? Or on the given rather, not the problem? Is there an added information that you can place in here? None? Sige. So if you have none, then your required information is the composition and amounts of the exit streams. So you have 2 exit streams, the raffinate and the extract. So it's asking for the composition and amounts of the exit stream. Okay, how do we do it? Go to the solution. Okay, as for our solution, there's a need for us to determine any of the two. You either determine the X sub AM, the composition of A, or the composition of your bulk phase M in terms of A, or you can use XCM. Because any of these two you can use in your equilibrium diagram. And since we're more interested on the solute, then we'll have the XAM. Okay? How do we determine this XAM? We will, of course, use the material balance equations. Okay, so we will do that. Just erase this one. This is the thing that we are interested in. Overall material balance tells us that L sub O and V sub N plus 1 should be equal to L sub 1 plus V sorry, L sub n, because we're now talking about multi-stage system, and V sub 1, which is also equal to M. Now, in our problem, our feed is 200, our solvent is 600. So you will have 200 plus 600 is equal to L sub n plus V sub 1. And that is also our M. So L sub n plus V sub 1 is equal to 800. So this is our first equation. If I'll do component balance on A, how will I do it? So I will have LO XAO plus V sub n plus 1 Y sub A n plus 1 equal to M X A M. If I want to know the CM, the X sub CM, then this should be XCO, and this should be Y sub CN plus 1. If I intend to use component C in my component balance. But in this case, we use A. Just substitute what is given in the problem. So you have 200 and you have 0.25. You have V sub n plus 1. Your V sub n plus 1 is 600. And just so happen that it's pure, so it's 0. This one is 0. And you will have your M, X, A, M. But what is M? This M is the sum of LO and V sub n plus 1. Also, it could be the sum of L sub n and V sub 1. So I can place here 800 X, A, M. Now, in this particular equation, I'll be able to solve X sub A, M. Now, we need to know that in our plotting. So let's say you have 200 times 0.25 divided by 800. That would be 0.0625. We have 0.0625 for XAM, for our XAM. Now you may wonder why. What's the purpose of the XAM? Okay, so I will draw our triangular diagram here. For now, we won't need the lower rectangular diagram. We just need the triangle. And let's say I'll have in the base envelope. So this is a problem that will require both equations and equilibrium diagram. Now, in our problem, it says that our L sub O has 0.25 as its is it acetic acid? Let me check. Solute is acetic acid. Okay, that's it. So if it's acetic acid and it's 25% and then water, it does not have any solvency. Remember, this is A and this is C. So if your LO is 0.25, then A and no C, just water, then it must be somewhere here based on my drawing only. So based on the actual equilibrium diagram, of course, it should be different. This is 0.5 and this is 0.25. So this is your L sub O. That's where your L sub O is. Now your solvent is 100% isopropyl ether, so it should be here, just like what I've explained a while ago. It should be on the apex of the triangle because this location signifies 100% C. This is 0. Okay, now this is your V sub n plus 1. What you do, you connect these two. You connect the V sub n plus 1 and the LN. Okay, that's it. Now, the point M will be plotted on the line that connects these two. So you have the line that connects L sub O and T sub 1. M will be anywhere on this line. and you'll be using the computed XAN, and that's 0.0625. Now, approximating that one, if this is 0.25 and this is 0.12 something, half of that would be 0.06. You go up, that would be in this case very steep. So I'll just use this one class just for illustration purposes, okay? Just for illustration purposes. So let's say this is the location of M. Again, how did we get it? The X sub AM should be the one that we have computed, 0.0625. 0.0625. Okay? On the horizontal axis for the A, you locate the 0.0625 value which you computed, you project it up on the line connecting L sub O and P sub N plus 1. Okay? Now, what will you do? You will have to, in this case, it says here that you have 3% acetic acid in the raffinate. Where will you use this? So I'll just use another color. Oh, this one. Okay, where will you use it? So the 0.03 or the 3% acetic acid in the raffinate, you locate again in here. So this is 0.5, 0.06, so this must be 0.03, just on an approximation. And what will you do with the 0.03 class? You project it up in here on this part of the phase envelope. This one has an X A N, which is 0.03. You locate the 3% here on the horizontal axis. You project up until you are on the lower part of the phase envelope. If you recall our discussion regarding the location of the raffinate points on the phase envelope, it's on the lower part. The extract points on the phase envelope is on the upper part. So that is why upon looking, after you have determined the 0.03 or the 3% here on the horizontal axis, you go up and project that particular composition on the phase envelope. Okay? Now, I think you would know what is expected now. So this is your L sub N, this one. That's your L sub N. So for you to be able to determine the extract, you just go up. Go up, connect this L sub N in the lower part of the phase envelope with the M, and then extend until you rest here on the upper part of the phase envelope. And this is your V sub 1. Your L sub N and your V sub 1 should pass through the M. And since you know the L sub N, you can find the V sub 1. Knowing that this is the location of the V sub 1, you can give the required information of the problem as to the YC1, because this is for the C, and in here, you will have, just extend it here, the YA1. A, because in here you have A and in here you have C. So where your point is, you just read on the vertical axis the composition of the C for this extract and the composition of the A also for this extract. Your B, your YB1 will be 1 minus YC1 plus YA1. That answers already the question of the composition. So it will answer the requirement, the composition of the exit phase. Okay? As for the raffinate, since you're just given one composition and you have already projected it here on the lower part of the phase envelope, you just need to read here you just need to read the XCN. This one. This is C, right? So from in here, you'll get the XCN. From in here, you have the XAN. It's given in the problem. So your XBN will just be 1 minus XAN, which is given in the problem, plus XCN. Whatever that is, kung ano di mabasa mo sa kilid, kaya ang C mo are sa vertical axis. Now, these two already answers the first requirement of composition. Now, if I'm going to ask you, how will you be able to find the amounts? The amounts of the extrude and the raffinate layers. How will you find the amounts? You already have the compositions, right? From your material balances. So how will you find the amount of L sub n and V sub 1? You do component balance. You do component balance. So let's say you have XAN times N is equal to L sub, here you copy this one. You have LO and V sub N plus 1. So what you missed, what you are actually finding is the L sub N and the V sub 1. So you place it here. L sub N, X sub AN plus V sub 1, Y sub A1. You know this, right? You have determined that. You know this to be 800. The L sub N you do not know. But the X sub AN you know because you have read it in here. There is a kilid. There is a dalom. By the way, this XAN class is not to be read on the diagram because this is given in the problem. This is the 3% X sub AN. It's the YA1 that you're going to read here in your diagram. For this point V1, you read the A composition here on the horizontal axis. That would be your YA1. Okay? You have that. You have two unknowns. But you can relate these two based on the overall material balance. We know that 800 minus L sub N is equal to V1. So this V1, you change to 800 minus L sub N. With all the things known, you can determine the L sub N. Once you have the L sub N, the V sub 1 will just follow. Now, we can't use a specific computation here. I'm just giving you the procedure because the equilibrium diagram that I'm using here is just a hypothetical self-drawn diagram. We should be using the exact equilibrium diagram for isopropyl, acetic acid, and water system. But nonetheless, please let me know if you can follow the discussion or the process of determining what the problem requires. Do you get it? Naintindihan ang process? You have any questions? So it says here composition and amounts. So the solution to the problem, this problem is both analytical, though mostly analytical, but we need one part in here, this one, which is graphical. You need to plot the L sub N here and connect it with the M, which you have computed, the X sub AM or the X sub CM to locate the M, and then find the location of V sub 1. After that, the rest will just be very simple because you need only to substitute to the formulas that you have made. Any question? No question? Now, I'll go back to our slide. Okay, this is our sample problem number 7. Now, we'll go to the formula in determining the number of stages because we don't want to rely on pure graphical approach in determining the number of stages. So your handbook, your chemical engineering handbook, has this equation 15-3 in page 15-20 of the 9th edition. This allows you to determine the number of stages, and you have here the variables that appear in the equation defined. Okay, so you have the mass of the solid per mass of the solvent for the X sub in, Amo gini siya ang pagkasulat sa handbook. And X sub out is the mass of the solute divided by the mass of the solvent in the raffinate. Okay? Y in is the mass of solute in the solvent. The mass of the solute in the solvent. Of course, it's with the carrier solvent. Your K, the capital K that you see here is Y over X. For dilute solution, this Y over X is equal to the slope. Okay, to the slope of the equilibrium equation. So if you're given an equilibrium equation for your system, then the M for that is the K as well. But that is for dilute solutions. Ano ang dilute solution? Solutions in which the solute is less than 10%, equal to or less than 10% in composition. Okay? What is this Y and X? Y is the mass of solute per mass of solvent in the extract. Now, and then X is the mass of solute per mass of solvent in the extract. Now, notice that they are written in capital letters, the X and the Y, so meaning they are not mass fractions, but rather mass ratios. Okay, you learned that in our chemistry. Whenever X is written small, then it's fraction. But if it's written big, it's ratio. So mass of solute per mass of solvent here for the X. Y is mass of solute per mass of solvent. It has to be that way, not mass fraction, but mass ratio. Okay? So everything else anyway here is defined. And that's how you determine the number of stages using the equation that is given in your handbook. Or you can use Grimser equation, which is really exactly the same as the Grimser equation for stripping. The Grimser equation for stripping, the opposite of gas absorption, and the Grimser equation for liquid-liquid extraction is the same. So you can see here, you have the ln of x sub 2 minus y sub 1 over m divided by x sub 1 minus y sub 1 over m. M is the slope of the equilibrium line. Okay? Y sub 1, what is y sub 1? It's in here. The composition of the solvent. Because this particular formula uses the orientation that points below the equipments are 1 in subscript and points above the equipment has a subscript of 2. Points, or rather I'd like to use phases, not points. So the phases in their subscript. So you just have to follow this. The A is still the absorption factor. The absorption factor that we have discussed in gas absorption. And you'll be able to determine the number of stages for your extraction system. Okay, so you have two alternatives, this one and this one. Anyway, this one is also found in your handbook, the Grimser equation. Now, if in gas absorption or stripping, we made use of mass, or rather mole ratios, rather than mole fraction, we can also use that in here, especially if the phases, the amount of the phases that we are using are the inert parts of the phases only. Like for this instance, your L prime here is just the carrier solvent of your feed. It does not take into account the solute. That is why it's L prime. It's just the carrier solvent. Okay, the V prime is the amount of your solvent without the solute. The amount of the solvent without the solute, meaning if you have 100% pure solvent, then that is V prime as well because it does not contain your solute. Okay, so you have here L prime, V prime, L prime, V prime. In lieu of the, this is liquid extraction, in lieu of the mass fraction, you use the mass ratio. Okay, mass ratio ni siya. Okay, 1 minus. So meaning if you have a two-component system, 1 minus the composition of one of the components is of course representing the composition of the other. So you can use the overall material balance. You can use the overall component balance as long as you indicate the component that you use in balancing. And you can use this one. you are making use of the inert part of the phases, the L primes and the B prime. So L prime in this case for the feed is just the carrier solvent of your solute in the feed. B prime, B prime is to be viewed as the diluent for your solvent. So meaning minus the solvent, what is the diluent present? That would be your B prime. Or if your solvent contains your solute, you take away the solute from that particular solvent, that would be now your V prime. The V prime that you have in here and the V prime that you have in here are the same. The L prime and the L prime that you have here is the same. If you have an aqueous feed, your L prime is just the water content of your feed. Okay? If you have a pure solvent, your V prime is the volumetric flow rate that is given in the problem, as is, because your solvent does not contain the. Okay, so just like gas absorption, you have three formulas to use. Okay, now let me check. Okay, we still have minimum solvent and then we have the sample problems again. Now, in this particular problem, I'd like to check whether this is coming from John Lisa. Just give me a few minutes. The problem that is shared to you in here is the exact problem that is found in John Putli's on page 796, and it's the sample problem 12.7-3. Telling you of an inlet water solution of 100 kg per hour which contains nicotine with a weight fraction of 0.01, meaning this is a dilute solution. It has to be stripped. So your nicotine is with water and it is to be stripped using kerosene strip. Notice the term that was used. This is a process of stripping because you are taking your solute from a liquid phase. So comparable to stripping, you take the component of interest from a liquid phase, so stripping. Although in the case of stripping or desorption, as an opposite to gas absorption, the phase that takes out the solute from a liquid phase is gas phase. That's desorption and stripping. But in here, that term was also used in this case, even though your solvent is liquid as well, same as the feed which is liquid. So sometimes there are books that would say the formulas for stripping or desorption is similar to formulas in liquid-liquid extraction because of the fact that the solute will be taken out from the liquid phase. Okay? So your water, your nicotine, rather your water is to be stripped, meaning you need to probably take out a pollutant in the form of nicotine from your water stream using kerosene. So the kerosene contains 0.0005 weight fraction nicotine. So in this case, the solvent has a very minute negligible amount of nicotine also present on it. Now, it is desired to reduce the concentration of the exit water to 0.001 weight fraction nicotine. So since it says here it is desired to reduce the concentration of the exit water to, so concentration of the exit water to 0.001. Okay, so this refers to the composition of the raffinate. The exit water phase is the raffinate. The solvent phase, the exit solvent phase is the extract. So we plan to reduce the concentration of this exact exit water to 0.0010 weight fraction nicotine. Determine the theoretical number of stages needed, and you are provided with the equilibrium data as follows, where X is the weight fraction of nicotine in the water solution and Y is that of kerosene. You need to plot first your equilibrium curve for this liquid-liquid extraction. You may wonder why there's a need for you to plot because you're given here the XY pair of data. the purpose is for you to have the equilibrium curve, or if it is a line, the equilibrium line plotted based on this pair of x and y. Okay? From that particular equilibrium data, you are to determine the theoretical number of stages. Now, of course, we don't want it to be graphical. We want it to be analytical. So this problem can be solved using the analytical approach. And that one is already here in your book. It's in here in your book, the solution. And it could also be solved using the graphical approach. In both ways, the results agree with very negligible difference, variation in the two results. Okay? Let me check. I will just clear my napkins. So for your dry lab this afternoon, so you will have something to do. Since most of the time we have nothing to do with dry lab, read on the solution of this particular sample problem. Okay, that would be your share of the things that we need to do for this week, since last Tuesday we're not also able to do it. So we'll just compensate it for now. Now, we go to minimum solvent flow and optimum L prime and V prime ratios. Determination of the minimum solvent flow for liquid-liquid extraction or extraction is the same as determining the minimum solvent flow for stripping or desorption. They're just the same. Even the procedure is comparable to that of gas absorption. The only difference is, in this case, class, we have the process of liquid-liquid extraction. We have two liquid phases. In the case of stripping and gas absorption, we have the liquid phase and a gas phase. But as to the principle behind and determining the minimum solvent flow, which also will help us determine the optimum solvent requirement or optimum ratio of the feed to the solvent, then it's the same in principle as gas absorption and stripping. So you have this figure in John book here indicated as to how we determine the minimum solvent flow for extraction. The optimum is 1.2 to 1.5 times the minimum solvent requirement, the inert part of the solvent that is. So it's either 20% or 50% more of the inert part of your solvent. That's your minimum solvent, that is. That would be now your optimum flow rate. So for you to be able to know the optimum, you first need to know the minimum, because once you have the minimum, you just multiply it with either 20, 1.2, 1.3, 1.4, 1.5. But we tend to maximize it, class. In computations, I suggest to my student to use the 1.5 multiplier. So meaning we're using 50% of the determined minimum solvent requirement to be our optimum solvent to use in our process. Okay, what is the principle behind minimum solvent requirement for extraction? If you look at the diagram that is being shared to you in here, it's the same as the diagram in gas absorption and stripping. The only difference is that in gas absorption and stripping, you have another operating line in here on top, and that's for your gas absorption. In here, since we have stripping, so our operating line is below the equilibrium line or equilibrium curve. The stripping operating line is comparable to the extraction, liquid-liquid extraction operating line. How do you exactly place its location under the system's equilibrium line or equilibrium curve? You just use the mass fractions, x1, y1, x2, y2. So 1 in here at the bottom of our extraction tower and 2 for the upper part of the extraction tower. Once you have already the operating line, the minimum solvent requirement for liquid-liquid extraction is like this. You move this point of the X2 vertically until you reach the point P on the equilibrium curve or on the equilibrium line. This particular projection of X2 on the equilibrium line or curve will tell you of the allowable, or shall I say, amo na gini siya ang pinaka-maximum na mass fraction of A in Y2. And what is Y2? So if you look at Y2, Y2 is extract, equivalent to the representation of John Copley's to Y1. Okay? So if we project this point X2 vertically up on the equilibrium line or curve, we get the maximum mole fraction of A in the extract. We maximize the amount of the solute that is to be extracted. Whatever is that maximum amount, that corresponds to the minimum amount of solvent that will achieve such goal. If it's translated to Ilonggo, bala, ng sa amuni kagamay na solvent na akong gamiton, ano ang pinakadako na mole fraction sa solute na ma-achieve ko sa extract. So that's it. That is why it's labeled in here as Y2 maximum. With the minimum solvent requirement that I'm trying to determine, this will be the maximum amount of A that is possible for me to be recovered in the extract layer. Just a moment, guys, ha? Now we go to this one. For minimum and maximum solvent to feed ratios, I just place in here the specific equations that you have in your handbook. The 8th edition, I have indicated that these equations are taken from the 8th edition. So you will be able to determine either the minimum or the maximum solvent to feed ratios, meaning with the corresponding amount of the feed, what would be the minimum solvent as stated in the problem based on these ratios. And it's and you can look it up on this section of your handbook in this particular equation. So it's not only, this equation does not only allow you to determine specifically this one. This is for the minimum, the equivalent for this in the graphical interpretation, but the equation also allows you to determine the maximum solvent to feed ratios. Okay, if you have your handbook, please look it up. If you're using the 9th edition and you can find this particular equation in the 9th edition, probably you need to just look for the section where liquid-liquid extraction is and look for the equivalent. You can use the basis of the soft copy of the 8th edition of your handbook, which is readily downloadable online. What I mean is you get the equation from the 8th edition. If you don't have it, copy it and then try to find that where it is in the 9th edition, because I'm sure they are not located in the same sections already, or they are not numbered in the same way. Now, this is the last part of extraction actually, and this is the easiest part. That is why I place it in the last part. This allows you to use the extraction factor, given here is the formula, allows you to use the extraction factor in determining the fraction of the solute remaining in your feed using pure solvent in single stage extraction. So meaning class, this is already the formula that will tell you how much of the original solute remains unrecovered in your feed if you're going to use a pure solvent in a single stage extraction system only. Now, where can you find this formula? You can find this formula in McCabe, and I have indicated here the equation and the corresponding example, which is easy to follow using the formula that is specified in here or indicated in here. Now, in the formula, you just need to determine the extraction factor. The K sub D is the distribution coefficient. The V and the L are the flow rates of the solvent and the feed respectively. We represent the V as the solvent and L as the feed. Now check your McCabe. You should have a copy. If you don't have a copy of your McCabe, download a soft copy of it and check on this particular example that uses these three formulas. So easy to follow formulas. Only good for problems that requires you to find the specific informations indicated here. So if you want this information, this is the formula. If you want to know the fraction of the solute recovered, so this one, the solute remaining. This one is the solute recovered using pure solvent also. In a single stage extraction unit, then this will be your formula. Both are dependent on the extraction factor. Okay? Now, you could see in here that I have sample problems, and these same sample problems are hyperlinked to the PowerPoint presentation and shared to you in your Canvas. Please read on these sample problems. They are not as difficult to follow. The procedure is not as lengthy as designing our equipments. Okay, it's just determining the K and determining the percentage of solute remaining or solute recovered, or even the number of stages. So here, please read on this. I will not explain it anymore because I have placed here the solution. You just read on this on your spare time or in our dry lab schedule later, together with that particular sample problem which I also asked you to read. That way we have finished already extraction, and you need only to listen to the recording of leaching and membrane separation. Not so much to worry about membrane separation because they are more on concepts, not much on computation. Okay, I'd like first to go back to the slide. So this is our slide on the sample problems, and in terms of efficiencies, though, how efficient is your particular equipment, extraction equipment specifically, I have indicated here the equations in your handbook. Though we may not be able to cover it in our subject, specifically under this topic, because this is already added information, a great bulk of information in liquid-liquid extraction. You have already its location here in your 8th edition, in the 8th edition of your handbook, as to finding the efficiency for your extraction tower, the overall stage efficiency or the Morphy stage efficiency, and the overall stage efficiency as related to the Morphy stage efficiency. Please just look this up, okay, in your spare time. Anyhow, when your time of review comes, this will help you as well find it easily. Okay, your Z, we have discussed this one, how to find the Z using the HETS. Remember in the problem on designing our column, wherein we determine the diameter based on the flooding velocity, then followed by the height, in which we use the HETS. In your handbook, this is the equation, the equivalent equation that you can use. I just place it in here so you have something from your handbook which you can check, or you can cross-check together with what is written in Gian Puplis, because the source of that particular sample problem is from Gian Puplis. Okay, and that ends already extraction. Expect that I will be uploading the recording for leaching. I'm just finishing the editing, and then I will share it with you, maybe if not tonight, tomorrow, the leaching and the membrane separation. Just listen to it, the recording, and read the PowerPoint presentation. Should you have any problem with it, don't hesitate to message me. Now,